7C, confidence intervals for population proportions. So up to this point with confidence intervals, we dealt with population means. You know, the average that we're looking for. What's the average age? What's the average grade? Et cetera, et cetera. Now we're going to deal with population proportions. The proportion of people who want a certain thing. The proportion of items that are a certain way. So that's population proportion. We use a lowercase p for population proportion. So that's a lowercase p. And if you remember in the past, we've used lowercase p for probability. Well, proportions and probabilities are very much related. If the proportion is 0.97, then the probability of selecting that thing is 0.97, or the area under the curve is 0.97. So it makes sense that the population proportion p is the same value as a probability. So we got lowercase p. Well, if we're going to find this new thing, this population proportion, then we need a point estimate for that. And the point estimate, so I'm going to put that as population proportion, just so we have it labeled up here. And we're going to use p hat for the point estimate. If you remember from when we were dealing with linear regression equations, we said that when we put a hat on a variable, that means it's an estimated value. So a sample proportion is an estimated value for the population proportion. And that sample proportion can be given to you in a few ways. One way is it can be given to you as the number of successes over the number of trials. X items out of n total. So our sample size, how many of the items in our sample will give you the proportion. That will become a decimal number. Another way it could be given to you is as a percent converted to a decimal. So you could be given a percent and convert that to a decimal. 27% would be a proportion of 0.27. So that's another way it could be given to you. And it could be given to you as a proportion, 0.36. So it can either be given to you as the number of successes out of the number of trials. So you take a sample of 48 individuals. Of those 48 individuals, 21 believe such and such. 21 over 48. Divide and you get your decimal for your sample proportion. It could be given to you as a percent. You take a sample of 92 individuals. Of those 92 individuals, 18% such and such. So it's given to you as a percent, you convert it to a decimal. Or you take a sample of 126 items, and the proportion that do such and such is 0.93. So you have to be careful when dealing with confidence intervals for a population proportion to make sure you recognize whether you're given the number of successes out of a number of trials, if you're given the percentage of a number of trials, or if you're given the proportion of a number of trials. And you can't judge it by being given n, because you'll always be told the sample size. So that's not what is going to make the adjustment for you. It's going to be where you're told the number of successes, where you're told the percent, or where you're told the proportion as it is. So just as with our confidence intervals for the population mean, we have to know what table to use. Well, luckily for us, when we're dealing with a population proportion, we will always use the z-distribution. So anytime you're dealing with a population proportion, you're going to use the z-distribution. Now, technically, there is a little calculation that we should do to verify that we can treat it as a z-distribution. but we never treat it as a t-distribution. So that calculation that we do is we take n times p hat, and that has to be greater than 5, and we take n times q hat, and that has to be greater than 5. Now we know what p hat is, that's the sample proportion, so I guess the question is, what's q hat? Well, q hat is the complement of p hat. So that's just 1 minus p hat. If p hat is 0.37, then q hat is 1 minus 0.37 or 0.63. So we've got that. And we do this calculation to verify that our distribution of proportions can be treated as approximately normal. Now in this course, I'm not going to require you to do this calculation. In fact, if you do this calculation, you find out that it comes smaller than 5, still do the work because I intend for you to do the problem. Okay, I'm not going to intentionally give you something that doesn't work for this, so you say, oh, can't do it. So assume it can, and realize that this number of 5 is actually pretty much arbitrary, meaning some people will tell you that this product should be greater than 5. Other people will tell you it should be greater than 10. And it's really dealing with how precise do you want to be. It's just like dealing with confidence intervals. Do you want to be 90% confident, 95% confident, 98% confident, 99.997% confident? So same thing here. The larger this value that you use to determine it, it's just saying how much more sure you are that it can be approximated as a normal distribution. The smaller this value, the less normal the distribution, which means you may be a little bit in a gray area and your results may be a little bit fuzzy. Okay? So, but we're always going to assume that this works. We can always use a z-distribution. Now, since we're dealing with a confidence interval, then we're still looking at a point estimate plus or minus a margin of error. So we're still looking at, we're not looking at x bar, now we're looking at p hat minus a margin of error, and p hat plus a margin of error. So same as we've been doing with the other ones. The question is, how do we find that margin of error? Okay, and to find the margin of error, you say E is equal to z sub c times the square root of p hat q hat over n. So now this will be our margin of error formula. Z sub c found the same way as it has been in the past. We're going to look at the confidence level and then go look in the table to find it. P hat is either going to come from x over n, a percent being converted to a decimal, or being given directly the decimal, the proportion. Q hat is going to be 1 minus p hat, and n is our sample size. Okay, so that's what we're looking at. So there's our margin of error. This is how we compare it to our proportion. So believe it or not, we're ready to try a problem. So I'm going to erase some of this, get it out of my way, so we have somewhere to work. And I'm going to throw some of the equations off to the side here, so we still have them available for us to see. So we're going to say that q hat is equal to 1 minus p hat. We're going to say p hat is equal to x over n. And remember, there's the other ways we can find it, depending on what we're given. And then the margin of error is equal to z sub c times the square root of p hat times q hat over n, the sample size. So we want to find a 95% confidence interval for the population proportion, or for the proportion of people who think that remote learning is a great way to take classes. We take a sample of 37 individuals. So n is equal to 37. of those 37 individuals, 10 of them say that they think that remote learning is the way to go. That's X, it's our number of successes. Okay? And believe it or not, that's what we need. 95% confidence interval for a population proportion P. We got our sample size, we got X. So now we start finding things. Well, P hat is equal to X, 10, over N, 37. 10 divided by 37 gives us 0.27. Approximately. It's actually 0.270 repeating, if we want to be specific about it. But I'm just going to leave it at 0.27. Well, Q hat is equal to 1 minus 0.27 is equal to 0.73. We need Z sub C. Well, if it's a 95% confidence interval, we're going to go into that bottom corner, 0.95, and that gives us 1.96. And now that we have that, we have everything we need to find our margin of error. Margin of error is equal to Z sub C, 1.96, times the square root of P hat, 0.27, times Q hat, 0.73. And just to take a moment to point out, notice that these will always, if we were to add these two numbers, they're multiplied together, but if we were to add those two numbers, they should add up to 1. So that's a little sanity check to make sure you're doing things right. This number plus that number should add up to 1. But we're going to multiply those two numbers. Over N, 37. Be careful of order of operations in this. You have to do everything in the radical first, take the square root, then multiply by 1.96. Okay, so 0.27 times 0.73 gives me about 0.1971. Divide that by 37, gives me 0.0053270, with the 270 repeating. We take the square root of that, which gives us about 0.073. Then we multiply that times 1.96, and we get 0.14. So E is equal to 0.14. So now that we have our margin of error, we can now find our confidence interval. Remember, it's our point estimate, so in this case, P hat minus our margin of error, and P hat plus our margin of error. So P hat was 0.27, 0.27 minus 0.14, our margin of error, and 0.27 plus 0.14, our margin of error. 0.27 minus 0.14 is 0.13, so it's 0.13. And 0.27 plus 0.14 is 0.41. And then the last step, just as it always was in the past, we want to state what we're doing here, so that's a 95% confidence interval for P. And notice that's why it's so important that we have to include what it's for also, because we were dealing with the population mean U previously. Now we're dealing with the population proportion. And we always have to give that confidence level. So that's our process. We look through this, we pull the information out, 95% confidence interval for P, we look and see what the sample size is. Were we given the number of successes? In this case, 10 out of 37 people said such and such. That's X over N, giving us our P hat. We might have been given that out of 37 people, 27% said that they thought remote learning was the way to go. In which case 27% turns into 0.27 when you turn it into a decimal. Hey, that works too. Or we might have been told that of 37 people, the proportion of the 37 people who thought remote learning was the way to go was 0.27. So we always have to look to see where do we get this information from. Now, I am going to take a little side thing here and say, let's look at that little test I told you about. Can we say that this is approximately a normal distribution? So I'm just going to take n times p, and I'm not going to bother, well, I will. All right, n times p is equal to n is 37 times p hat, actually, p hat, 0.27, 0.27, which is, so 37 times 0.27 gives you 9.99, which is greater than 5. And then n times q hat is equal to 37 times 0.73, which is going to be equal to 27.01, which is greater than 5. If you don't believe me, 37 times 0.73, 27.01. I'll give you a little hint on that. When you're doing these, those two will add up to whatever your sample size was, okay? But notice here, remember I said that this 5 was arbitrary? We're fine here. Both of these are larger than 5, so we're okay with this is approximately normal. But notice if someone said we want it to be greater than 10, we're skirting the edge. We're not quite at 10 here. So if someone said it had to be greater than 10 for us to treat it as approximately normal, then we're sunk. We wouldn't be able to do this.